All right, forces. So we already talked about static forces. The one thing that I didn't get to mention in the previous videos is something that's called a free body diagram. Okay, and it really is exactly what its name implies. It's a diagram that's free of the body. In other words, you're going to be reading a question and it might be a crate that's being pushed across the floor. It might be a cart that's being pushed across the floor. It might be an elephant that's being pushed across the floor. No matter what it is, we draw it as a little box, okay, with the force coming from its center pushing on it. Okay, so we don't draw the elaborate elephant or the elaborate car. Okay, we just draw a box. Now, in some books, they use a dot and they have all the forces coming out of the dot. I tend to use a box because then I can put the mass of the box inside. Okay, but so all of the forces then come from the box going in different directions depending on which way they're acting. Okay, so it's called a free body diagram and we'll be using it a lot. So it's simply a diagram showing all of the forces that's free of the actual body. So whether it's a person, a car, or an elephant, it's going to be a box. All right, so it's time to look specifically at some forces. There are 3 forces that you encounter every day of your life, really probably almost every second of every day of your life. And the first one we've already kind of talked about. It's called the force of gravity. We talked about it when we were doing our lab, right? It was gravity that was pulling it down, but we've talked more about the acceleration due to gravity than we have the force of gravity. So it's called the force of gravity. It's also known as the gravitational force, and sometimes you'll even hear the gravitational force of attraction, because gravity always pulls things towards the object that's creating that gravity. Gravitational force of attraction, force of gravity. Now, for all forces, no matter what they are, the symbol that we use in high school physics is a capital F, with a subscript to tell us about what's causing that force. So the force of gravity we write as a capital F with a subscript G, okay, and that G just means that it's the force of gravity. Whereas if it was the force of friction, it wouldn't be a G there, it would be something else. And we'll get to friction in time. So I'm thinking you all know what the force of gravity is, but if you were in front of me and I asked you to define it, I'm not so sure you'd get it right. You'd probably say maybe something like it's the pull of the earth on objects, right? And it is. That's why if you step off your bed in the morning, you get pulled down to the earth. It's why if you hold a ball up and let it go, it gets pulled down to the earth. It's the force of gravity or the gravitational force of attraction that the earth is putting on that ball or on you. And I think earlier we talked about the fact that Sir Isaac Newton was key in figuring this out. And he had a hard time convincing people that an object could put a force on another object without actually touching that other object. So there's that famous story of the apple fell on his head. Did it really fall on his head? Probably not. But he was probably sitting somewhere and saw an apple or something fall and began to ponder what made it fall, because nothing was touching it. And he believed, and you'll learn about this when we do his 3 laws of motion really soon, he believes that an object wouldn't just move on its own, that if it moved, there must have been a force applied to it. So if you think back to our kinematics unit, we looked at all the changing motion of objects, an object accelerating, an object slowing down. But nowhere did we say what's making that object accelerate, what's making that object slow down. The only way you can actually change the velocity of an object is applying a force to it. To overcome, remember, its inertia that we talked about the other day. So the force of gravity then, you might think, is the pull of the earth on an object. And you wouldn't be wrong, you just wouldn't be quite right. Because I would say, well, then what about why is the earth revolving around the sun? And hopefully you would say, oh, from gravity. But this time it's the pull of the sun on the earth, right? It's not just the earth that can apply a force of gravity or a gravitational force of attraction. The sun can too. And maybe you've heard that the reason we have tides is because of the moon's pull of gravity on the earth. So clearly the earth is not the only thing that has gravity. And thanks to Sir Isaac Newton, we actually know now more clearly what gravity is. He developed something called Newton's law of universal gravitation. Okay, and there's one thing in it that's really, well, actually, there's several things in it that are really cool. But one thing in it that most people, the unphysicsed among us, don't know. And that is that any and every two objects in the universe exert a gravitational force of attraction on each other, as long as they have mass. So any and every two objects in the universe that have mass will exert a gravitational force of attraction on each other. So right at this moment, I'm exerting a gravitational force of attraction on you and on the people in Australia and on the people at Dairy Queen eating, going through the drive-through to get, what are they called, blizzards, and the people at FHS and the people all over the world. Okay, and so are you. So any and every two objects in the universe exert a gravitational force of attraction on each other. And the equation where we can calculate that is Fg is equal to G m1 m2 over r squared. Okay, where m1 and m2 are the masses of the objects, are the masses of the two objects. And of course, mass measured in kilograms. R is the distance from the center of one object to the center of the other. Distance from the center of one object to the center of the other. Measured, of course, in meters. Now you might say, why is it an R if it's a distance? So imagine that the two objects are two of you that are seated in my class a safe 6 feet apart, right? One of you could get up and walk around the other one. And as long as you stayed 6 meters away, this force wouldn't change. So really it's called R because it's the radius of a circle where anywhere on the circumference of that circle, this force would be the same. So that's why it's called R. The other part that's important to notice is the center of one object to the center of the other. So if I pick two of you and I measured the distance between you, it really wouldn't make a lot of difference if I put my meter stick like on one belly and then measured to the outside edge of the other belly, or if I pushed it in to get to your center, to the center of the other. None of us, our centers aren't that far from our outside edges that it would make a big difference. But if I was doing it for you and the earth, so here's the earth, and here's you standing on the earth, and I was trying to figure out the gravitational attraction between the two of you, it's going to make a big difference if I measure from the center of the earth to you, or if I only measure to the outside edge. So we always say center to center, okay? So that's the R. The G is a universal constant, and we're going to run out of time. Universal constant. Universal means it's the same everywhere in the world. Universal, everywhere in the universe.